Okay. Hi guys. So it's 8. We'll just start first. Yeah. Okay. So we're doing DC circuits today. This chapter can be kind of broken down into two main parts. So you have your circuit analysis, which is like anything that deals with circuits, and then you have just some ideas about like voltage and current and electric field. So these are the main two parts of the chapter that we'll be going through today, lah. So we'll first start with some basic stuff. So kind of assumes meter. So ampere is 4 meters voltage child should know. You probably resistive. That's what I use. So resistivity is usually defined as rho and conductivity just the inverse of it. And it's just sigma. And the definition is here. Yeah. So oftentimes this is useful because you want to calculate things like resistance of a continuous object, such as a circular frustum, for example. So if you have two faces of a circular frustum here, it's a bit laggy. That's okay. Uh, can you guys see the stream? Loading. Oh, oh god. Okay, okay. Sorry. Give me your. Okay, can you guys see it now? Okay, nice, nice. Okay, so so we'll go back to this part. So why is resistivity and conductivity important? Because if you have random weird shaped materials like this resistor over here, you can simply use this and find your infinitesimal resistance, dr, and integrate over it. And this can be defined using your resistivity. So you usually can write something like this and integrate over it if your resistances add in series. So this is one example here, and you can see that the result is actually quite nice. So yeah, so that's for this part. It's just your normal integration, basically. In contrast, if you have a case where your resistances add in parallel, then you will need to, you can find something like 1 over R. So this is for parallel. It's something like 1 over R equals to the sum of 1 over dr, which is, you can write something like this. So then after that, you invert this result and you will get what you need. So it just depends on the situation. You need to visualize how, depending on how you slice, whether the small resistances add in series or parallel. So yeah, just a note, just don't always assume that it's in series. Yeah. Okay. So next we have Ohm's law. So this is the basic relation, but there's another form of Ohm's law which you might not have seen before, and this is J equals to sigma times E. So here your E is just your electric field as per usual, but your J here is probably the new thing. It's called the current density. So it's basically just, so you can just think of it as this current divided by area that's passing through. So if you have some random area here and you have some current, then yeah, you can define a current density based on this setup. So these two equations are actually equivalent, but you use them in different situations. So it's quite clear that this one is in circuit analysis. This one is when you want to deal with E-fields and stuff like that. So yeah, it's quite important to know what form of Ohm's law to use, even though both are correct, because one of them is most certainly more useful than the other. Okay. So we also have the definition of current as the rate of flow of charge, or even more rigorously, you can think of it as the flux of the current density. So this is similar to how we define things like our gravitational flux before. So remember that this was defined as this. So yeah, it's quite similar in a sense. Or you can also think of your electric flux, both work. Okay, so these are all just definitions. Small remark, zero current does not imply zero voltage, and zero voltage does not imply zero current. So this can be a bit trippy because you might be tempted to think that because V equals to IR, right? You might think that, okay, if I equals to zero, then V equals to zero mathematically. There are situations where this isn't the case. Similarly, you might think that, okay, given this equation, if V equals to zero, then I must be equal to zero. Okay, perhaps the second one is more clear because it's possible that R equals to zero, and that's the case of a short circuit. But try to think of an example to prove the first one. So I will leave this as an exercise to you. Usually the examples that prove these involve some funny things like short circuits, as I mentioned, or open circuits, or like even like infinite resistance, which we'll see later on in the notes what it is. Okay. Here we have an example on how to use the other form of Ohm's law, which you might not be that familiar with. So here we have a cable with two cylindrical conductors of radii A and B. And basically what is happening is that the current is flowing radially. You can see here through the cylinders. And you want to find effective resistance. So of course, if you have to do something 1.1, we could have just like this, the because of these as your slowly like that. So this is perfectly valid. But integrals like that, the approach is using Ohm's law. So what you want to do is you want to suppose that of R is flowing through the total current goes through on the current radial distance from R. And based on this, so you found E as a function of R. Now, if you want to think of resistance, right? When you think of resistance, you usually think of potential. But now you have electric field. So it's easy to find the potential in this case because of this relation. So now all you have to do is just integrate over all the radii to find the potential difference. And you can find V in terms of I. And because of this means that this is just your R effective. as desired. So this method is equivalent to just integrating resistances. If you wish, you can try using the method. Yeah, but it's the same thing. Okay. Uh, the next part is kind of small, might not come out that frequently, but it's on IV characteristics. So this is basically just a graph of I against V. And of course, for a linear resistor, you expect that it's a straight line passing through the origin. But for non-linear stuff, it might get a bit weird because you can get random curves like this for your IV characteristic. So something like this curve here, you can see that obviously the resistance is not constant. And to evaluate resistance, you want to evaluate V over I at that point. Now, what exactly does this mean, right? So instead of thinking of it as the gradient of the graph, you should think of it as finding a point. Let's say I take this point here. Oh, cannot see. Wait. Okay, it's exceptionally laggy today. I don't know why, but okay, let me try again. Uh, okay. Is the stream or is it visible? Oh, okay. Okay. Let's see if that helps. Let me start it again. Okay. What about now? Okay. Nice. Okay, so back to okay, I'll see. So I want to emphasize that when you evaluate resistance, you always evaluate it in the over one point. And this clearly not seen as clearly not because this is dV over dI, but that is clearly not V over I. So you need to be a bit careful about this. So writing Ohm's law like this in terms of infinitesimals is wrong by definition. It's not dv over di is meaningless. So so this okay. We will move on to talk about the EMF. So about the EMF is not the charge around. So yeah, now you write it in terms of infinite. So voltage can be because this now you electromagnetic different out there. So it's defined and the hand formulas here for ohmic resistance to just remember. And sheet and so power is usually negative. Yeah, because the source of dissipating power. So yeah, power calculation. Okay. Another thing that might be useful and probably might not be as familiar is the maximum power transfer theorem. So this one is basically the statement is basically you want to maximize the power that is transferred to the load resistor, which in this case is the small r, and small r can be freely adjusted. So what is happening here is quite simple actually. You just want to find the power in the small resistor in terms of a function of small r, and you differentiate instead equals to 0. Interestingly, you realize that the max power occurs when the load resistance equals to the resistance of the circuit. So small r equals to big R. And this is what we call the maximum power transfer theorem. So yeah, you might not really see this applied a lot, but it's just there, so you should know it. Yeah. You should also just memorize the results so you don't have to go around deriving this every time you need to use it. Okay, so that's on that. We'll move on to the more important part of the chapter now on circuit analysis. So in circuit analysis, the objective is to find currents and potential differences. So there are many ways to do this, but we'll just introduce like a few tricks or methods that are more commonly used or like can be applied to basically everything. So first of which is the voltage and current divider rules. In here, it's quite simple. You can just prove these using Ohm's law. Yeah, for voltage, you just want to distribute the voltage evenly such that it scales with the resistance of the potential, such that it scales with the resistance of the 2 points it is connected to. For current, it is the opposite. You want to scale it like that. And yeah, in practice you don't need this, but it's just good to be faster by using these. The more important one is probably Kirchhoff's laws because these are like the fundamentals. So there are two main laws here. You have KCL and KVL. And the first one, KCL, is more fundamental. Basically, if you add up all the currents entering or leaving a node, you should get 0, accounting for your sign conventions of the current. So in circuits, usually there's no like fixed sign convention of doing things. You can assign signs arbitrarily as long as you're consistent with how you do it. So In this handout, what I did was I assigned outgoing currents as positive and incoming currents as negative. So we will just stick to that for the handout. Yeah. If you want to know why this is true just because of the conservation of charge. You cannot create any extra charge at a node. So anything that comes in must come out, basically. So that's KCL. The other one is KVL, Kirchhoff's voltage law. Basically, the sum of potential drops across a loop is zero. Now, you can just think of it as potential. If potential is defined, then if you go in one whole loop, there should be no potential difference. So that's basically what the statement is saying. Usually we assign signs as positive for potential drops from positive to negative, and negative for potential gains from negative to positive. So that's the usual sign convention that we use. These are the two basic laws. In practice, you can get away with just using these two laws and spamming it on every circuit you see. But there are usually better ways to visualize things, and that is why we are introducing nodal analysis and mesh analysis here. So nodal analysis is the first way of visualize. Oh, the stream died again, I think. Okay. Oh no. Okay. Let me check. Yeah, let me just try restarting the stream. Okay. Nice. Thanks. Okay, yeah, just let me with the data. Okay. Uh, so yeah, as I mentioned, the first way of visualizing circuits is nodal analysis. Here, our focus is on voltages. So we look at the nodes in the circuit, which are basically your vertices sort of thing. Yeah. So what you want to do here is you want to assign potentials to these nodes in the circuit. But potentials by itself, they don't have any meaning. Only potential differences have meaning. So what we can do easy, eventually the nodes become zero potential. And that will make the math much easier to do. So yeah, so once you do that, once you set some nodes to be grounded, you can assign other nodal voltages and you can assign other nodal voltages to other points. So these are your unknowns in this case. Here you can see that all the nodes below are zero. And we assign the unknowns V1, V2, and number of unknowns that we need to write. Now, once you do this, what you're left to do is to apply KCL as many times as you can. What you want to do is, for instance, let's focus our attention on, okay, for instance, let's focus our attention here on this, on these nodes. Okay, so let's do this. What if the sum of currents is zero, right? So by convention I defined earlier, outgoing current is positive. So let's say you have this current here. You have this here, and you here. Some are considering the potential differences. So that's what we did here. Yeah. So you can see that this 4 amps is given to us. And for the other two currents, we basically just take the potential of the node we are considering minus the potential of the adjacent node divided by the voltage between them. And yeah, this point is potential 12, just to make things more clear. These currents are possible. In this case, the other point that we're repeating it is here. And this is what we call a supernode because it contains a voltage source within. So when you come here, then you have some current here. Then you have another in the current, and the sum of 1, 2, 3 must be equal to 0. So yeah, the sum of these four must be equal to 0. So that's what we did here as well. So yeah, once you get the hang of how to do this, then it should be quite simple. And you just form this set of simultaneous equations and you can solve them. You eventually obtain the desired current that you want. Oh wait, I see that the stream close to it. But let's uh, is the stream back? Stream is okay. Okay. I'm not sure what's happening because it's not even allowing me to start a stream now. But okay. Let's okay, let me just leave the call and rejoin. Should be back. Okay. Okay. Can. Okay, nice. Okay, I'm not sure how much of it got captured just now, but basically, okay, quick recap. When we do nodal analysis, we look for points or collections of points to apply KCL to, and you just want to consider all the currents that come from these points, and you want to sum them equals to zero. You want to take care of sign conventions, so usually what you are recommended to do is you just assign everything as positive, and you want to find the current in terms of the potential at the node you are considering minus the potential of the adjacent node divided by the resistance joining them. You want to add all of these terms up. And if you consider it this way, there's no way you'll mess up the sign convention. So this is the best way to consider it. So yeah, the sum of this equals to zero. So this is the guideline. Okay. So once you solve your simultaneous equations, you have obtained everything you need to know about the circuit because you have all your potentials, which means that you can find all the currents that you want. So that's the nice thing about this method. The next method is mesh analysis. So instead of looking at the points, now we look at the loops or what we call the meshes. And instead of looking at potential, we look at current. So what we want to do is instead of assigning arbitrary potentials, we assign mesh currents through each mesh. And the recommendation is again to assign clockwise mesh currents. In reality, you can just assign any direction you want as long as you are consistent with your signs. But the easiest way to not mess up your signs is to just assign everything as clockwise. Now, what you want to do now is you want to find the current through each circuit component. So what do I mean? Is In the meantime, can you guys hear this? Holy shit. Can you guys hear this? Okay. 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 Change of plans. I'll just try streaming from my computer. See how this works instead. Okay. Testing. Okay. Can you guys hear me here? Nice. Okay. Okay. Let's switch to this. Okay. Okay. Yeah. Alert me if the stream dies again. Yes. Okay. So we were we were here. Yes, we were here, mesh analysis. Okay, so like what I was saying just now, what you want to do in mesh analysis is basically you found all the currents through each individual circuit component, and once you have that information, you want to write KVL for everything. Yeah. So for instance, in this example, the easiest current you can spot is the I2 because you're given this constant current source of 2 amperes this way. But your I2 points this way, which means that your I2 is negative of 2 amperes. So yeah, sign is important here. But you want to look at the other two loops here. It might be a bit more complicated because you have this random 5 ampere current source in the middle of nowhere, and this kind of affects how your mesh currents are defined, right? But things can be solved if you just consider what we call a super mesh. So just like a super node, you also have super meshes. In this case, your super mesh is just this whole thing, here. So now to work around this 5 amperes, you notice that your so in this way, right? Your I1 is going this way, your I3 is going this way, and your 5 amperes is going this way. What this means is that taking into account direction, I3 minus I1 equals to 5 amperes. So this relates your I3 and I1. And now you can set up KVL using the super mesh. And okay, I kind of skipped some steps here, but the way to do it is the KVL gives, so you go around this loop, uh you have negative 38 here plus 4 I1 minus I2 plus 1 I3 minus I2 plus 3 I3 equals to 0. This is your KVL equation for the super mesh. This is because this is the current through R1. This is the current through R2. And the current through R3 is simply I3 because it's not shared with any other meshes. So this is how you set up KVL when you have resistors that are shared between meshes. Basically, you want to find the real current that is flowing through in terms of the mesh currents. So to reiterate, mesh currents are not necessarily the real currents that are flowing through components, especially the components that are shared between meshes. So yeah, if you want to find the real current flowing through that, you need to consider the current through each mesh, and then you subtract them. Yeah. So this is equivalent to this equation here. And once again, it becomes a thing of solving simultaneous equations. So yeah, both nodal analysis and mesh analysis eventually reduce to simultaneous equations. And that's kind of a elegant thing as compared to bashing out Ohm's law for everything and keeping track of all the potential differences. I think it's much easier to just bash out simultaneous equations at the end. Okay, so there's much more practice for both nodal and mesh analysis in the problem set. We can go through some problems later if time permits. The next thing is on source transformations. This is a quite simple concept. Basically, it just states that these two circuits are equivalent. And if you ever need to, you can just transform one into another. And I think this is also quite easy to see because this is just a consequence of Ohm's law. Both of these circuits will give the same current flowing through here. Oh my god. Yeah, the same current flowing through here of just V over R. Now, why is this important? Because sometimes it's easier to visualize or simplify circuits when they are in one form. For example, here you have a random circuit that's quite complicated. And if you just try to do things normally without knowing any source transformations, then it gets kind of hard, right? Because like how are you going to visualize where the current and everything goes? But now that you have source transformations, what you can do is first you transform everything into one type of source. So for instance, here we do everything into current sources. Then you get this circuit here. Now when everything's a current source, things become easy to add because first of all, your resistances are like in parallel. Second of all, your current just add like that in the big loops outside. So you can deal with each part of the circuit separately, and you get this, and you get this. So yeah, so your resistance here is just in parallel, and then your currents were just added or subtracted based on the direction. So now the circuit's really quite simple. But at this point, you can also do a reverse transformation back into a voltage source, which is easier to combine them together because you effectively have two standalone circuits that are in series with each other. So when you have two circuits that are in series with each other, it's easier to convert back to voltage. And once you do that, you can add up these in series. You can add up these in series also, and you get a very simple circuit. So yeah, source transformations can be quite niche, but I think it's also quite useful when you have a lot of random, especially when you have a mixture of a lot of current sources and voltage sources that you're given. Then it can be quite useful to just make everything into one type of source and work it out from there. Okay. Uh, there are some ideas, but most of them just involve like ways to find resistance for complicated resistor setups. So the first one is on the delta Y and Y delta transformations. So the idea is quite simple. You can have a setup like that. So this is the one in blue in the figure. So this is the delta configuration. What it states is that you can always convert between a delta configuration and a sort of Y configuration like that. You can always convert between these two using a formula. And this is quite useful because when you deal with circuits of a oops when you deal with circuits of a delta configuration, it's usually very hard to deal with. For instance, if I gave you any random network, let's say you had a resistor like that, you had another resistor like that, uh, then like you have like God knows what resistors here, stuff like that. Then it's quite difficult to deal with delta networks. But once you transfer them into star networks, Y networks, uh, it can be easier to deal with because, for instance, you can add this with this to create a new resistance, that type of thing. So it's usually very situation dependent on whether you want to use this transformation. But anyway, the transformation is given as such. Uh, there's a sim okay, there's a pattern to this, so there's a simple way to remember it, but you can just remember it however you want to remember it lah. Uh, so the special case is if all three resistances are equal, then your delta configuration is exactly 3 times the resistance of the Y configuration. So that's That's just the delta Y transformation. To prove this, the proof is actually quite simple. All you need to do is just know how resistors in series and parallel work. So what do I mean by this? Well, if you want to, okay, let's say I'll just outline how the proof works. Let's say you have this. Okay, I will not write the resistor symbols to just to save some time. Let's say you have this, and let's say you consider 2 points here between B and C. It can be connected to some voltage source or anything. Okay, this configuration here gives you an effective resistance of simply RB plus RC, because this branch is useless. But in this configuration, your effective resistance is the same as RAB plus RAC in parallel with RBC, which is, now this is just RBC, RAB plus RAC, RAB plus RAC plus RBC equals to R effective. Now the key is that you assert that these two configurations are equal, so their effective resistance must be equal. So you can now write RBC plus RAC, RAB plus RAC plus RBC equals to RB plus RC. Okay, so you have one equation here. Now, the thing is, if you repeat this same argument over any two pairs of points, you will get two more equations, right? So let's say you connect points A and B, you get one set of equations. You connect points A and C, you get another set of equations. And they'll look something like this. So they'll look something like this. And yeah, basically what you can do is you can just solve these three simultaneous equations. Easiest way to do that is just add them all together, and you can derive your transformation. Yeah. So that is kind of the outline of the proof. You can see that I didn't need to know anything other than how series and parallel works. So it's quite elegant actually. So I would still recommend you to just remember it, because speed is everything. But in the event you don't remember it, you can always prove it very simply. So there's nothing to worry about. Yeah. Oftentimes the delta to Y transformation is more useful, as I've mentioned earlier. Okay, the next idea is equipotential points and symmetry. So this is quite important idea, because in resistor networks with many resistors, you can easily kill off a lot of resistors if you know how to apply symmetry. So what does this mean? So in this example here, you have this kind of square where all the points are joined by resistances. So there are a lot of resistors here, right? But the very nice thing about this square is that it's symmetric here. So because it's symmetric here, what you can do is you realize that this point kind of maps to this point. This point also kind of maps to this point under the symmetry. And in that sense, because it's so symmetric, you can just ask yourself a question, right? If you consider, this part here and this part here. Under such a symmetric situation, would there be any tendency for current to flow in these two blue indicated regions?
blue indicated wires. And I think it's quite obvious that the answer is no, because, well, there should not be a tendency for current to favor one direction to another if we have argued that the whole setup is symmetric. So, because of that, you can assert that no current flows between points that are symmetric like that. And so, what you have done here is you have basically killed off these points. So, yeah, if you redraw the circuit diagram, you can see that the circuit diagram is like that. And what I've done earlier is I've killed off these points here because we asserted that no current flows. Because no current flows, you can just do anything you want with these 2 points. And I've connected them with a wire. Similarly, because no current will also flow through the wire, even if the resistance is 0. So now once you do that, you can see that this circuit is very easy to evaluate because it's just series parallel combinations. And you can just evaluate it and get the answer that you need. But the point of this example is not the series parallel combinations, it is the argument on why you can just kill off resistors like that. And yeah, it's quite important to understand this because whenever you have symmetry, your goal should always be, so when you have symmetry, your goal is, can you kill off resistors by looking for equipotential points, which are basically points of the same potential. And if you can, then replace with wires of 0 resistance connecting them, because it doesn't matter, no current will flow through anyway. So yeah, this is the point of this example. These pairs of points are equipotential to each other, and that is why you can do this. There is another example later on how to spot equipotential points in the problem set. So I think it'll be more concrete when I go through that part. Okay. Next idea is on current injection and superposition. So when we deal with stuff like infinite networks, it's quite important to know how to do this because you can always just like anyhow assume adding current into one node and removing current from another node. And you can superpose these situations together and try to analyze what happens to the potential difference between the 2 nodes. So here we have an example of an infinite square array, right? So how we do this is we add current into one node. So let's say we choose let's say we choose these 2 nodes. Let's say we put a current I in this node, and then we remove let's not remove it first. Let's just consider putting a current I here first. So what happens to this current? Well, because this grid is infinite, so the current just spread out evenly like that. I over 4 in each direction. And the other node we wanted to consider is here. So we have gotten that I over 4 current flows from this node to the adjacent node. And this contributes a potential difference of IR over 4. So that's putting in a current I. So we asserted that putting in current I contributes delta V equals to IR over 4. So that's our first assertion. Okay, so that's the first scenario. Now let's look at another scenario that's quite similar. Let's consider this adjacent point, but now we remove a current I from it. And by the same logic, because the grid is infinite, so a current of I over 4 must be coming from each of the adjacent points in this way. So now you see here that Now you see here that current I overflow flows in the same branch again, in the same direction, and once again contributing IR over 4 potential difference. So the second observation is that extracting current I contributes IR over 4. Okay, so now we have these two contributions. Now let's say we superpose the two cases together. What does this mean? That literally just means you add up the two cases because potentials are additive. So we have a current I here entering and a current I there exiting. And now, so why do we choose to superpose these two cases? Well, because this is the same thing as connecting these 2 points to, oops, because this is the same thing as connecting these 2 points to some voltage source, right? So if you connected these 2 points to some voltage source, what will happen is that a current I is entering from the left point and the current I is also exiting from the right point. And because of that, superposing these two cases together will give you the exact setup you need to calculate the effective resistance. So now once you superpose this together, the V total is just the sum of the V's. So it's just this. And the total current that is flowing is I, right? And you recall from Ohm's law that, uh, okay, recall from Ohm's law that this relation is true, where R effective is the effective resistance between the 2 points. And so you can simply conclude that R effective is just small r over 2. And that's how you solve the infinite grid problem using a ingenious superposition argument. So if you read here, this is exactly what I did. And yeah, you realize that the setup is actually quite symmetric because both cases of putting in and extracting current actually contribute the same potential difference. So that's quite nice. Yep. So that's on superposition. There are also more examples on superposition in the problem set. The next type is on basically self-similarity in infinite networks. So what is self-similarity? Self-similarity just means the circuit contains itself. So you can see here this infinite circuit. Well, clearly it contains itself because if we cut it here, then everything here is just the circuit itself. So the circuit literally contains itself. What this means is that, so here is R, here is R. What this means is that you have this. These two circuits are equivalent. It's equivalent to just R effective because the circuit contains itself. Now this is the key observation that you're supposed to make for this infinite circuit. Because once you do this, you can set up an equation in terms of R effective by simplifying this. So this is what I did here. So R effective equals to R in series with R and R effective in parallel. And you get a quadratic equation in terms of R effective, which you can solve to get the physically meaningful root, which is positive resistance. And you actually get the golden ratio somehow. So yeah, so this is the effective resistance and how to calculate it for infinite ladders. There are many variations of this you can do. One common one that I've seen is this. So you can have a infinite ladder like that. So you have resistances in your powers of 2, you just keep going on. So this is also quite interesting generalization of it, lah. Because your whole ladder scales by a factor of 2 as you go between steps. This can be so if you want to challenge yourself, you can try this. Yep, to infinity. I think I'll probably post this on the Discord afterwards, like the solution to this. It's not in the problem set, but this is just an interesting generalization. Okay, the last idea that we need is negative resistance. So in gravitation, you see negative mass. So negative resistance is actually quite similar. So of course, negative resistance doesn't exist, but it's just something that we introduce to help ourselves when symmetry is broken and we want to restore it and then superpose. So the two cases you need to spot are connecting R and minus R in series. Of course, this is just zero resistance. But when you connect R and minus R in parallel, then you have this, which is 1 over 0, which is infinity. And infinite resistance is just open circuit. Arguably, the second one is much more important, and a few examples below will show you why and how to use it. So here we have another example of another infinite resistor network. And the way to solve this is very, very similar to how we solved the one with the square grid. Basically, you want to put current in, take current out, and when you put current in, you have I over 6 going from each. Oops. Uh, yeah, when you put current in, you have I over 6 flowing in each branch here. So you have I over 6 here. When you take the current out, you have another I over 6 here. This will give you I over 3. So uh yeah, this will be your potential difference is R over 3, which is equivalent to I times R effective. And R effective is just R over 3. Now this should be quite standard if you just refer to the square grid example if you're not sure how this works. Okay, but the other case is more interesting because now we cut the wire between nodes A and B. So what happened here is what happened here is more interesting. Now this thing is gone. So how would you find the resistance in this case? Now the thing is that you know the answer to the previous part in a very highly symmetric scenario. You know that the resistance is R over 3. So part 1, R effective is R over 3. But in the scenario where this thing is cut, you see that everything would have been symmetric if the thing was there. So why not we use the idea of negative resistance to put the thing back there, but compensate with another resistor, in this case the negative resistance. So I argue that this is equal to A connected to resistor R and negative R to B with everything else following. The key idea is that a resistor R and negative R in parallel is equivalent to a cut of wire. So this is the key idea, or just an open circuit. Yeah. And you realize that once you do that, you restore the symmetry because you can just take this one, and by taking that one, you can use this result back. And you basically have the initial grid from part 1, along with a negative resistance of minus R in parallel to it. So your new effective resistance will simply just be R over 3 times minus R over 3 minus R. Now you can check yourself that this actually is positive, and you should get R over 2, which is positive. So your negative resistance actually doesn't make things negative. It's just a concept that helps you visualize how open circuits work. So to reiterate, is the concept. This is the concept, yeah. Whenever you have a cut wire, replace it with a negative resistance in parallel with a positive resistance. It gives the same thing. Again, the problem set has more examples to illustrate this. So yeah. Okay, so that's the end of the notes. I think at this juncture, do you guys want to take a short break or continue with the problems? You guys can just message in the chat. I'll just look at it. Okay, can. Okay. Uh, I'll just start with the problem requests. So the problem requests were 11 and 12. So okay, let's start with these then. Okay, so for 11, we have a bunch of resistors here. Now, this kind of looks similar to the problem where we use symmetry just now to simplify a lot of things. In this case, the symmetry is like that, in this way. And because of this symmetry, now you can argue that from the symmetry alone, these 2 points are equipotential, the ones in blue, and they are basically the same point. These 2 points are equipotential as well. The ones in blue here, C, and so on and so forth. So let's just label all the points for completeness. These 2 points will be E, the same point because they're equipotential. These 2 points are F. This is G. This is C. Oh wait, no, let's not use B. Okay. Uh, okay, let me just relabel everything, but you get the point. I hope. Okay. Okay. This is okay. So this is C. This is D, D, E, F, F, G, G, H, I, I. Okay, so there's a whole bunch of equipotential points here, solely due to the symmetry. So nothing else, just symmetry. From symmetry alone, and because these points are kind of the same thing, right? You can just redraw the circuit. And well, it's kind of tedious, but I'll just like show how I do it. So I usually just start by drawing one point here. The leftmost point is A, so I just draw it here. Now, A is connected to C by 2 resistors in parallel. So you have this. Okay, I will just not write the resistances because all of them are the same. So this is the start of your circuit. Now, C is connected to D by 2 resistances also. So you can also write this. At the same time, C is also connected to E by 2 resistances in parallel. Oh, oops. Yeah. Okay. C is also connected to E by 2 resistors in parallel. So we can also do this. So this kind of is a thought process, right? You look at what point is connected to what point by what resistor, and then you just draw the combination like that. So just going like that, okay, we can just continue what we're doing. So E is connected to F by two resistors. We can draw this. And D is also connected to F by two resistors. So why not we just short F here, and then we just draw. So this also F. Then we have D. So we have this so far, and this is already the center. Now at this point, you can just see that, okay, this is the center, right? And everything is, there's also a symmetry axis this way. So we can just reflect this thing this way, and the rest of the circuit is basically this but reflected. Okay, so I'll just draw it for completeness sake. Okay. The other point is B. Okay, I can also just label this. This should be G, this would be H, and this would be I. So you can see here that this whole circuit has been simplified into this just by using the argument of equipotential points. And now once you have this circuit is just series parallel, right? Series parallel combinations, which is easy to evaluate. So the main point is not the series parallel, the main point is the argument on why, because there's a symmetry axis this way, you can just, due to the symmetry axis, there are a lot of points that are equal to each other, and you can just treat them as literally the same point and construct the circuit in this way. And this always works in general when you have equipotential points. When you have equipotential points in the circuit, you can treat them as the same point when redrawing the circuit, and you can get a new circuit like that. So that is the main idea. Okay. So okay, I'll just complete this. So the effective resistance is just 2 times of R over 2 plus, okay, all of these things are just R over 2. So 2 times of R over 2 plus uh 1 over 1 over R plus 1 over R. So yeah, so the final answer should be 2R for the effective resistance. Yeah, so that's for this question. The main point is the symmetry lah. Now if you don't spot the symmetry, I'm not sure how bashable it is by, like, I guess technically you can just, very technically you can just like combine these together and then you get this. So like very technically you can just make it into a bunch of like delta networks and then just transform it. But I think that's not very efficient. This way of spotting symmetry is much more efficient and gives you the same answer. So yeah, that's the trick for this problem. Yeah, I hope that helps. Okay. Uh, we will then discuss the other problem. This is arguably more interesting because it's for once not a resistor problem. Okay. So this one, the physical situation is that you have a space here which current can flow. So current, uh, control. Okay. Current flows here in this space, and you inject a current of I naught into A, extract a current of I naught from B. You want to find the potential difference. Okay. So first thing first, qualitatively. So let's look at this qualitatively first. How does a current lead to a potential difference here? So you start with current I, right? Then there's a whole bunch of things, and then you finally lead to potential difference. Now, to just complete the blanks, this should be quite simple. Current leads to a current density. Current density leads to electric field. Electric field leads to potential difference. So this kind of completes the chain. Once you have this qualitative understanding of how the problem works, then it should be quite simple because all you have to do is just join the gaps between this. So how does this work? So let's say we consider, I'm just going to draw the square out. Let's say we consider this case first. I naught is injected into A. So at the end of the day, we're going to do superposition again. We're superposing the cases where I naught is injected from A and the other case where I naught is extracted from B. So okay, let's just first consider I naught from A injected into A. So what happens to this current? Because this plane is infinite, so inf this plane is infinite and current can only flow in one side. What the current is going to do is that it will just flow in a hemisphere outwards. So it will just propagate like that outwards. That's what the current is going to do after going here. Which means that because it flows in a hemisphere, the current density is just I naught divided by the surface area of the hemisphere, which is 2 pi r squared. Now, from Ohm's law, this is equals to sigma E. So E equals to J over sigma, which is rho J. So this is the electric field as a function of the radial distance. So this is just this step, this is this step. So now once we have this radial function of the electric field, then to find potential we just integrate. So we can just do something like this. Yeah. So this is the potential as a function of the radius of the radial distance. But what we are only interested in is the potential difference between points C and D. So we want this. And you notice that this is square root 2a, this is a. So uh oops. Everything got shifted. Okay. Okay, this is root 2a, this is a. Wait, RD is a, RC is root 2a. So actually this here, we don't have to care about what this reference is, doesn't matter. This is simply just this. Because you have your two endpoints that you want to compare your potential for. So what you can do is just evaluate this. You should get this. So that's your VD minus VC contributed by the current I naught entering A. Now don't forget you also have a current I naught leaving B, but that's a separate case. You want to superpose it. And you notice that if you do that, if you work out the second case, then you're basically just doing the same thing as the first case because the whole setup is symmetric. So actually, VD minus VC is also the same. This is contributed by A. This is contributed by B. And superposition tells you that you can just add them together. So you just multiply by 2, you get this. which you can rearrange to get this. And yeah, that's the resistivity. So to recap what's going on here, we first start with a qualitative understanding of how a potential difference even arises. This is quite important when the setup is kind of complex because in this case it might be a bit uncertain at the start. Like, how come I put a current here and then there's a potential difference between two other points which the current is not even perceived to be going in and out of at. So it's quite important to get a qualitative understanding of why this is even happening. Once you have the qualitative understanding, you know that a current leads to a current density, which leads to an electric field, which leads to a potential difference. Then you can find out what all these quantities are and relate them to each other. And that's kind of how you're supposed to think for this problem. So yeah, I think the qualitative understanding is actually the most important here. Okay, nice. Uh, okay. In that case, these were the two requests. I will. Are there any more requests in the chat? I can just go through them like right now. Okay, if no one's requesting anything, I will go through problem 2.9 because I find there's one trick here that is quite interesting and that's actually appeared before in SPhL. Okay, so problem 2.9. So you have this circuit here. You want to find the value of RL that draws the maximum power from the rest of the circuit and find that maximum power. Okay, so at first glance, this circuit looks a bit sus because you have this random thing here that connects two seemingly uh two seemingly independent circuits. So you might be a bit like bummed, right? Like, how do I remove the existence of this thing to deal with the circuits independently? Well, the thing is that you actually can do that because in a wire that joins two circuits like that, this wire here, this wire here is not part of any big loop. So it's not part of a closed loop, right? If you try to draw as many loops as you can, just like experiment by yourself. Try to draw as many loops as you can realize that any loop that you draw containing this wire will never be a closed loop. And because current only flows in closed loops, this means that no current flows through here. No current can even flow through here because it can never form a closed loop. So why I say this is interesting, because this trick appeared before in SPhL. You can check out you can check this out. It's also a circuit problem. It uses the exact same trick to simplify the circuit. Okay, so with that out of the way, no current flows through here. What this means is that you can, in fact, treat the two circuits separately, and you'll be fine doing that. Okay, so that's nice. So how do you treat these two circuits separately? So the easier way to do it is actually nodal analysis. What you want to do is you can ground all the bottom to be all the bottom nodes to be 0. Okay, once you do that, this is 12. This is V1 over 5. And this is V1 because here. So this is also V1. And this you can't express it in terms of anything else. So you just call this V2. So now you have all the nodal voltages already. Okay, so nice. What you can find instantly is from here. From here, you can instantly see that this is true. where you have to be careful with the direction of I1 as defined in the figure. So I1 flows from left to right, so you take 12 minus V1 over 5. Okay, so now you have for one equation. The other equation will come from nodal analysis from the second circuit. So from the second circuit, uh, you just have to consider this part. Consider this part for nodal for writing Kirchhoff's current law. So for this part, you should just get V1 minus 0 over 40 plus V1 minus V2 over 8 plus 5I1 equals 0. And if you sub in your I1 from just now, your I1 is just 12 minus V1 over 5 over 4, which is just 60 minus V1 over 20. Now you sub this in, you will get V1 over 40, 60 minus V1 over 4 plus V1 minus V2 over 8 equals 0. Okay, so you have another equation here. Another equation you can get is consider this point, perform nodal analysis again, write KCL, you will get this. Yeah, so that's your other equation. So now you have two equations, and you technically have three unknowns, but it doesn't matter because you're maximizing something, so that's fine. Two equations, three unknowns is fine because you're maximizing something. So you can rearrange these equations. And what you want to do is you can find V2 as a function of RL, and uh, then do this. Because you want to find the maximum power, and the power depends on V2. Oh, sorry, D power. Yeah. Okay. So we can do a bit of rearranging. This will be, if you do a bit of rearranging, you will get this. So your power is just this, because your V2 and 0 are the potentials. So the potential difference is V2. So your power is this. You get RL. Okay. So you can differentiate with respect to RL. You will get 36000. So you can solve this, you will eventually get this. This is the RL, and the corresponding PL max, you can plug it in and you get this. Okay, so uh so the main lesson from this problem actually is not really the circuit analysis or the power calculations. The main lesson is knowing that no current flows when you have a random wire connecting two seemingly independent circuits. No current can flow when, okay, so current cannot flow if you have 2 points that are connected by a wire, and that wire cannot be part of any closed loop. So once you see that situation, instantly just cross out that wire, assert that no current flows in it, and then treat the two or more circuits independently and solve them. I think once you look at the SPhO problem, it will make a lot of sense. So yeah, do take a look at it if you can. Okay. Yeah, so after you do that, the rest of it is just standard nodal analysis and differentiation. Oh, okay. Problem 3.3. Sure, sure. Okay. Okay. Uh, so at first glance, this kind of looks like similar to problem 2.12 because you're taking you're putting in current, you're taking out current, then you're finding the potential difference between 2 points which are not the points that you put in current and take out current at. So it looks kind of similar. But why do I say it's not as easy? Because in problem 2.12, the plane was infinite. But in problem 3.3, the plane is not infinite because your current is coming and taking your current is going in and being taken out from the sides of the plane. So plane is not infinite here because these are the sides. Now what implications does that have? Because it's the sides, right? So you can't just assert that, okay, and I'm taking current and extracting current from a random point in infinity. Here I'm putting in current and extracting current from the side of the plane. And for a plane, there's this thing called the boundary condition. Basically, it states that the current density must flow parallel to the edges of the plane at the edges. And it's not automatically satisfied when you have a situation like this. So what do I mean by that? Right? So I'll just draw it out here. Uh okay, A C O D B, and all the distances are D. Okay, so the boundary condition, as I stated, current density must be parallel to the edges of the plate. So it means that for instance at this point your current density must point like that and like that sort of thing. Now why is this so? Well, this kind of comes from your properties of conductors. So recall from the previous chapter on electrostatics, conductors, right? Uh, when you have like basically your conductor, because J is sigma E, so J is parallel to the electric field. Which means that this boundary condition asserts that your electric field must be parallel to the edges, which is kind of the case you expect a conductor to behave in. Because if it wasn't, then like it kind of fails the conditions, right? Does that kind of make sense to you? Okay, okay, can. So with that out of the way, if we assert that this like if we assert that the current density must be parallel to the edges of the plate, then we can see that okay, if we have this random configuration here, there's no way that putting in a current like that without any other current source or sink will result in the current just flowing parallel to the plate. So to fix this issue, what we are going to do is we're going to introduce this idea of image current sources. So it's quite similar to how image charges fix the boundary condition. Here, our image current sources will fix the boundary condition. But what exactly are we going to do? We're going to duplicate this 4 times, or three times. Okay. So I think this is quite a niche trick, but yeah, I think quite important to know to visualize like what boundary conditions are. I'm going to duplicate this 4 times. I'm going to create two things here. This is at 2D. This is at 2D also. So let's call this B prime. Let's call this A prime. Okay. Initially you had a current of I coming in from to A, right? Now because you have this new oh oh no. Okay. Okay. Now because you have this new setup, your current I initially just went to like half of space, right? Because it only went to one side. The plane is only on one side. Now you have two sides you can go. So instead of just putting I, you have to put in 2I. And once you put in 2I, half of 2I will go into the real plate that you are considering, which gives you back the exact same situation as just now, as like the real situation. So that's what you need to do to make the image situation replicate the real situation. So you need to multiply all the currents by 2. In a similar vein, the things coming out from B must be 2I. Now, what is the symmetry here? So you have B prime and A prime. So perhaps the most probably the easiest symmetry you spot is just extracting 2I from B prime, putting in 2I from A prime. And this is actually correct because if you look at it, this whole setup now is very symmetrical. Right? You have 2I coming out from both B and B prime, which are kind of opposite of each other. And then you have 2I coming in for both A and A prime, and these 2 points are kind of opposite to each other. So if you kind of draw uh what the current density looks like in the plate, you actually get something like that. So these are just like, so imagine I'm drawing like few lines kind of thing. If you draw current density, it's gonna look like that. Uh something something like that. Uh yeah, not very good at drawing, but yeah. Oh, okay. Then for the real side, it's gonna look like that. Yeah. But it's something like that. You can kind of mentally complete the rest of the image, hopefully. And yeah, so you can see here that because this current configuration is so symmetric, right? That at the points that we are considering, definitely the definitely the current density will only point parallel to it because the component perpendicular to the edge of the plate is just cancelled out because of this symmetry. So for instance, at B, all these components will just cancel out. So this and this cancel out. This and this cancel out. You're only left with components parallel. And that's why your current density at B will be parallel to the plane, exactly like what you want. So with this, we can assert that this combination of image currents satisfy the boundary condition that we want. And once you have once you realize this, the rest of the problem becomes really easy. It becomes very similar to what you have done previously. So uh so yeah, I hope this image configuration makes sense. Because if it does, then the rest of the problem is quite the same. Why it's half of 2i? Oh, okay. Because in your real plate, you're putting I in, right? But then your I only goes to one side because your plate's only on this side. Then there's also this side, but it's just gone. Yeah. So that's why it's a 2i. Okay, can. Uh okay, so now once you have this configuration, I'll just redraw it here. I Then it's quite a similar thing as just now lah. What you want to do is you find J, uh no, I, you start from I, then you find J, then you find E, then you find V, in this order. So your J R is just 2i. Okay, like consider one source. Let's say you consider this source. Your JR is just 2i over, because the in this case your plate has a thickness of T. So how your current will spread is that it will just spread like that. We just spread like radially outwards like that in a cylinder of thickness T. You can imagine how the current propagates in this cylinder. The radius of the cylinder just keeps growing. So uh so once you have that, your area in this case is just the curved surface area of the cylinder, which is this. So your current density is this. So same thing. Your E is this. You integrate. Okay, this is a reference point. Your R0 is a reference point. Okay, so you integrate. Uh, you will get this. At this point, it doesn't depend on what your R0 is, because you can find the potential at point C. You can find the potential at this point C due to the contribution of 1, the contribution of 2, the contribution of 3, and the contribution of 4. So all these 4 contribute some potential to C. And hence the potential at C is just rho I pi t times, you add up all your ln something something terms. Your first one will be this one is from, okay, this one is from A. Then you have R0 over 3D. This one is from A prime. Then you have you have negative here because your current is going the other way. Because your current is not entering, it's leaving. So instead of that, you have this, and this is from B and B prime. That's your total potential at C. And once you do this, your R0 actually cancels out. So it really doesn't depend on where your reference point is, as you would expect for a potential function. And you will get this. So this is your VC. But don't forget that in this case, you only considered A. You also have to consider B. So you also have to consider when the current leaves. Wait, no, sorry. Wait, my bad. Okay, you found VC, but you also have to find VD because your voltmeter measures this. So to find VD, it's actually quite simple because you already found VC and the whole thing is so symmetric. I think it is quite easy to see that VD equals to negative VC, and it will just be equals to this. If you're not convinced why it's just negative VC, you can just repeat the calculation. Yeah. Okay. So now once you have this, your final voltage that you want is just you can just write VC minus VD. That'll be this, and your rho is just this 5/3. Yeah, that's how this problem works. Okay, is this image current method used in any other questions you see? Uh, okay, there are a lot of. I think it's primarily used in problems like this, but there are a lot of configurations where this can adopt because this is actually a. I mean, this actually has real life applications. In real life, people usually measure resistivity of materials using methods like these. Like methods like these are actually legit, not just random setups. So you can have many different setups. Like for instance, you have okay let's think of a random one on the spot. Okay, for instance, you have a circle, circular disc, some thickness t, which is small, radius r. Then you can also have something like that, right? Then something like that also works. So like this is also another kind of situation, but this is probably much more complex because uh yeah, the circle doesn't have that kind of symmetry as the rectangle does. I think this is also something you can ponder about. I've seen this somewhere, but don't really remember the source. I can try to find it later. Yeah. Yeah, so other than questions like this, I can't really think of anything on the spot on where I've seen this before. But I think the main point of this problem is not really the image current method. It's more of just how to put things symmetrically to satisfy the boundary conditions. That's what I would call it. Uh, oh, wait. Yeah. I bet. Okay. I've seen this. Okay. I remember the problem wrongly then. Let me just like find it. Uh, okay. Never mind. Okay, the actual problem should be like that. Yeah. Now this makes much more sense. So yeah, now this is not equipotential. Okay. Uh, what the interaction between a wire and a ferromagnetic material? Huh? I don't know. I feel like this isn't circuits, right? Like it's oh yeah, but that's just EM fields, like how EM fields behave at an interface, right? Like okay, like this thing. Wait, what do you mean calculate the interaction? The force between uh wait, not really image current, right? Like you just have to find the this is just the induced current density on it. Okay, I okay, not really sure lah, but yeah, okay. This thing you will see will you ever see this? Okay, you'll see this, but not now. Okay. Do you guys have any other requests by the way? Cause if you guys don't have, I think we can just end slightly earlier today. Cause most of these are just like circuit practices. There isn't really like new insight other than just practice on how to apply nodal and mesh analysis. Okay, does I think it doesn't seem like it. So uh yeah, I think that's it for today. So thanks for coming. Be sure to try out some of these because I think nodal and mesh analysis needs a lot of practice now. So just try as many as you can, and you can send in your work if you want to. Okay, that's it for today. You guys can leave. Thank you.